Hey, what's up, guys? This is Chung here again. So this time, 1713. Minimum operations to make a subsequence. Pretty cool problem. Okay, so you're given like an array target that consists of distinct integers and another integer array that can have duplicates. So in one operation you can insert any integer at any position in this array here. For example, right, you can insert a 3 into any locations here, and you need to return the minimum number of operations needed to make a subsequence of array, right? So a subsequence, you guys all know, right? Subsequence has to be maintaining for some of the subset of the numbers that has also maintain the same ordering. And two examples, right? So the first one is like this one. So we have 5, 1, 3, and this is the array here. And we need to insert, since we only have 3 in the target in this array here, so which means we need to insert 5 and 1. That's why the answer is 2. And for this one, it's 3. Basically, we need to insert 3 numbers to make this target a subsequence of this new array here. And the constraints is like this, 10 to the power of 5. Here, target contains no duplicates. This is the key. This is a key like hint to solve this problem. So I think the first observation is that since we can insert any integers at any position in this array here, so the problem will actually comes down to what? Comes down to what's the longest common subsequences between these two arrays here. Because if we can get the longest common subsequence between those two arrays here, and then all is left is that we just need to insert the difference, right? The difference between the target and the length of the target minus the LCS. So the n is the length of the target. So for example, this one, right? So the longest common subsequence for the between those two arrays is 3, which is 1. And that's why since n is 3, n minus 1 will become to 2. Same thing for this one. So this one is a little bit more complicated, but the longest common subsequence between those two array is what? Is 6 6 to maybe 4. It's actually 6, 8, and 1. That's the longest common subsequences between those two arrays, which is 3. That's why the answer is 6 minus 3 is 3. Because, I think it's kind of obvious, because as long as we find the longest common subsequence between those two arrays, we just need to insert the remaining parts, the remaining the remaining numbers into this array at any locations, right? For example, we have 6, 8, 1 here. That's why we have 6, 8, 1. Since we can insert any numbers in any of the locations, all we need to do is we just need to insert the remaining parts, 4, 3, and 2, at the correct location, which is we're going to insert 4 between 6 and 8 here, and then we insert the 3 and 2 at the end of this array, which is going to be here. That's why the answer is 3. So now the question is, how can we calculate the longest LCS, right? Longest common subsequence. So a traditional way of calculating the LCS is by using a two-dimensional DP, right? So DP I and J, right? So I think there's another like LeetCode problem just for this LCS. I may be able to also make a video for that one. Basically for DPI and J, right? So I means the with first I's character in the array 1 and the first J's character in the array 2, what's the maximum like common subsequences? So here we have like basically we check if the I and J are the same. If they're the same, then we do a plus one. Otherwise, we do the maximum of I minus one J uh, dp, right? I minus one J or dp I J minus one, right? Yeah, actually this one is quite similar as the added distance, right? So dp this thing's I uh, so dp I minus one J minus one, right? And then we plus one, right? That's the traditional way of doing this LCS. But as you guys can see here, so the time complexity for this one is going to be what? It's going to be m times n, where m is the length for the first array and n is the length for the second array. And since we have like this kind of target, they're both like 10 to the power of 5. So if we calculate the LCS in the traditional way, we're going to have a TLE. So which means that we need to have like a better solution, right? And here's the key point here. The first one, the first one is like they're all distinct. So what does this one change? So what this one changes that for this one we can actually convert this sorry, LCS problem into a LIS, which is the longest increasing subsequence. And the LIS can be solved in the O of n log n time by using a binary search. And that's the key point to solve this problem. And so how can we convert this LCS to a LIS? Since each each element, each number in the target, they're all distinct, which means that we can create like a new array by using the index from the first target array here, which means that we're gonna have like 0, 1, 2, 3, 4, and 5. And then we're gonna replace the array with the index from the first target. Of course, if the array if the number does not exist in the first target, we just simply skip that. So then what we have from by replacing the index, we have 1, right? First one is 1 and 7 is not there, we skip that, and then we have 0. And then we have 2 is 5. We have 5, and then we have 3 is 4, right? And then we have 8 is 2, 6 is 0 again, right? 6 is 0, and 1 is 4. Yeah. So with this new array here, we can if we have if we not if we get the LIS, then the answer is the same. And the answer is what we have 0, 2, and 4. That's the LIS, right? The longest increasing subsequence for this one, which is 3. And why this thing works, right? It's all because and it's this is because since the numbers in the first array they are all distinct, and by using by using the index, right? Because since the index is always increasing, right? And if we can find the longest increasing subsequence, right, from the second array, then it means that we have find part of the subsequence, right? Basically, we're also find a subsequence from the target array because, like I said, they're all increasing. That's why as long as we find any increasing subsequence from the second array, it's also gonna guarantee to be a subsequence of the first array. That's why we can make this conversion. Yeah, and that's what exactly we're going to do here. So to make the conversions, I'm going to create a like index map, right? For like the nums of I, right? For each of the numbers uh, in the first target array. So in enumerate, right? And the target. And then with this index map, we can create a new array here. It's called A2 maybe. So the new array is gonna be the what? So we're gonna have like 4 nums in the second array, right? If the num is in the index map. Otherwise, I'll just skip that. Here, I'm just simply using the values from the index map, which is the index for that. Okay, and now we can just apply the ls on top of this A2. So the way we're doing that is by using a binary search. So we're gonna have like dp for that. So for num in the A2, and then we get the index. We do a binary search, right? Bisect left equals to dp dot num, and then if the index is smaller than the length of dp, right? We updated the dp by the current index. Sorry, by the current number. Otherwise, if the current number is greater than all the previously right numbers, we just append, right? Append to the dp, and in the end, the length of dp is the ls, and so that we can just simply return the length of the target, right? That's going to be the total minus the length of the dp, which is the ls. So run it. Yeah. And so the time complexity for this one is kind of obvious. So we have a n, and here that's n log n, right? That's why the time complexity is n log n, and the space complexity is O of n. Cool. I think that's it for this problem. I mean, this one is, I think it's kind of a classic one, as long as you can you can convert this problem to a LCS problem, and the next thing is that you have to be insightful enough to find this like constraint, which is going to be the one of the array is distinct numbers, and from there you just need to know you can convert this LCS to LIS if any of the array has like distinct numbers, distinct arrays or strings. And then from LIS we can do a unlog n. Yep, I think that's it. And I'll just stop here. Thank you so much for watching this video, guys, and stay tuned. See you guys soon. Bye bye.